What specific problem does the C-EVAL benchmark aim to address in the evaluation of course correction capabilities in LLMs?
The C-EVAL benchmark aims to address the lack of comprehensive evaluations of course correction capabilities in large language models, LLMs, following the generation of harmful texts. It quantitatively assesses how well LLMs can redirect their responses after initially producing unsafe content, thereby identifying disparities in course correction abilities among various models. Specifically, C-EVAL is constructed using 500 entries of harmful request and harmful response pairs, allowing for the measurement of corrective behavior through a defined methodology that includes sampling multiple decoding paths. The benchmark employs metrics such as TextCore@k and TextCore_TextMean to provide insights into how the volume of harmful content affects a model's ability to correct itself. Ultimately, C-EVAL serves as a systematic tool to evaluate and enhance the safety alignment of LLMs by focusing on their course correction performance.
Can you provide a detailed step-by-step breakdown of how the proposed method of course correction works, including the role of the synthetic preference dataset C-SYN and the triggers used?
The proposed method of course correction involves several key steps, starting with the creation of the synthetic preference dataset, C-SYN. First, C-SYN is constructed from 750,000 pairwise preference entries derived from harmful request, hour, and harmful response, FHR, pairs, emphasizing the importance of early course correction over delayed responses. The process begins by selecting 50,000 hour and FHR pairs from the PKU-safe RLHF dataset, followed by generating 6 ranked responses for each HR based on established value principles, which prioritize timely corrections. Next, the model generates initial harmful responses, IHR, by truncating the FHR at natural linguistic breakpoints, ensuring contextually appropriate segments. To facilitate course correction, a corrective trigger, T, is appended after the harmful content, guiding the model to produce a corrective response. For instance, a trigger like "however I cannot provide" prompts the model to shift towards a safer response. This method allows the model to autonomously generate corrections without needing external prompts, enhancing its ability to self-correct effectively. The success of this approach is validated through human evaluation, which confirms a 98% success rate in generating coherent corrective responses.
What are the key theoretical and practical advantages of employing the course correction method over traditional safety tuning methods in LLMs?
The key theoretical advantage of employing the course correction method over traditional safety tuning methods in LLMs lies in its ability to enhance model resilience against harmful content generation while maintaining overall performance. The course correction approach allows models to autonomously redirect harmful outputs, as evidenced by the observed improvements in course correction capabilities and resilience against jailbreak attacks after training with the synthetic C-SYN dataset. Practically, this method reduces the reliance on extensive human preference data collection, which is costly and can adversely affect annotators' mental health, by utilizing a fully synthetic dataset that prioritizes timely corrections. Additionally, the course correction method demonstrates a significant success rate of 98% in generating coherent corrective responses, indicating its effectiveness in real-world applications. Overall, this approach not only improves safety but also preserves the helpfulness of the models, making it a more efficient and effective strategy compared to traditional safety tuning methods.
How is the course correction capability validated using the C-EVAL benchmark, and what metrics are used to quantify its effectiveness?
The course correction capability is validated using the C-EVAL benchmark, which is constructed from 500 entries of harmful request, harmful response pairs, selected from the PKU-safe RLHF dataset. The evaluation process involves pre-filling the input with an initial harmful response generated by the model itself, allowing for the observation of potential course correction behavior. To quantify the effectiveness of course correction, 2 metrics are employed: text_core@k and text_core_text_mean. The text_core@k metric assesses how the volume of generated harmful content affects the model's ability to perform course correction, while text_core_text_mean provides an average metric for overall assessment. These metrics are calculated based on the proportion of sampled paths that exhibit corrective behavior after the initial harmful response.
What significant findings were obtained from the evaluations using C-EVAL, particularly regarding the performance disparities among different LLMs in terms of course correction?
The evaluations using C-EVAL revealed significant performance disparities in course correction capabilities among the 10 evaluated LLMs. Notably, LLAMA3 INSTRUCT and Phi3 Small exhibited high course correction performance, achieving approximately 90% on the core_mean metric. In contrast, a group of 4 models demonstrated poor performance, with core_mean scores below 20%, indicating a polarization in course correction abilities. Additionally, the results suggested that larger models do not necessarily outperform smaller ones, as evidenced by the varying performance of the 7B variant of Qwen2 compared to other models in the same family. Furthermore, the length of the initial harmful content impacted the model's ability to course correct, with longer harmful responses generally making it more challenging for some models to initiate corrections.
What are the main limitations or potential biases in the C-EVAL evaluation methodology, and how could these impact the interpretation of the results?
The main limitation in the C-EVAL evaluation methodology is the inherent bias introduced by using harmful response pairs, FHRs, derived from the PKU safe RLHF dataset rather than generating them from the test model itself. This bias increases as the distribution of the tested model diverges from that of Llama, which produced the FHRs. Consequently, the evaluation may not accurately reflect the true course correction capabilities of the models being tested, as they are assessed against potentially non-representative harmful content. Additionally, the methodology relies on a static evaluation setup, which could overlook dynamic responses that might occur if the models were subjected to real-time harmful prompts. To mitigate this bias, the authors suggest gathering relevant harmful responses for each tested model prior to evaluation, which would enhance the validity of the results.